Know this formula and use it. This summarizes many of the objectives that appear in mathematical frameworks, especially those pertaining to geometric measurement. Traditionally, state standards have placed much emphasis on the ability to recall geometric formulas and apply them accurately. We commonly find instructions such as solve, calculate, find the area, use formulas, memorize formulas, and so forth. This importance of knowing and applying geometric formulas is evident in the language of state standards throughout the nation, including Common Core. Far less prevalent, however, are phrases requiring students to understand and explain the geometric formulas that they are asked to memorize and use. In this regard, Common Core does set itself apart from other frameworks as it strives for a balance between skill and concept-based assessments. This Common Core standard, for instance, demonstrates the importance of knowing and applying geometric formulas. Looking at the second part of the standard, however, we see that students are expected to understand why the area formula presented in the first part of the standard works. The same can be found in other Common Core geometry standards as well. As evidenced here, Common Core's approach regarding geometric measurement goes beyond the usual theme of know this formula and use it, to include another aspect of equal importance. Teaching geometric formulas for understanding can be challenging for a number of reasons. For one, many students have come to understand mathematical competence as knowing what algorithms to apply and when. Discussions on why these algorithms work can be perceived as meaningless in this case, as they are an attempt to answer questions that students are not asking. Students are not accustomed to being tested on how well they understand the concepts that work behind the formulas that they know, so such material may seem extraneous when presented. Teaching geometric measurement formulas for understanding involves an adjustment on the part of the educator as well. Mindful of the limited amount of time they have to cover a wide range of state objectives, educators are unlikely to spend time on a topic that falls outside of those objectives. Thus, teaching practices become established over time, and they are difficult to change, even when conceptual understanding does become an important part of the state objectives. A third reason for this difficulty, and perhaps the most imposing one, is that geometric formulas are not always intuitive. While some formulas, such as the area of a triangle, can be understood relatively easily with the right drawing, explanations of others, such as the area of a circle, are much less obvious, and reserved as calculus topics in some cases. In short, presenting these complicated concepts in an uncomplicated way is no easy task. With these challenges in mind, ATI offers ideas and tools to assist educators with the task of presenting geometric formulas conceptually. As an example of a conceptual approach to teaching geometric formulas, we will revisit Standard 7G4. In order for students to see and understand the role of a circle's circumference in determining its area, we can begin by presenting a regular hexagon inscribed within a circle. The length of each side is denoted by S, and the minimum distance between side and center is denoted by D. After dividing the hexagon into 6 triangles, ask students to write an expression for the area of each triangle. Students are expected to write an expression equivalent to the following. Then ask students to write an expression for the area of the hexagon, stressing that all 6 triangles have the same area. Students are expected to multiply the previous expression by 6 and arrive at the following expression. To help students attach meaning to the expression 3s, ask, what fraction of the hexagon's perimeter does the expression 3s represent? Students are expected to recognize 3s as representing half of the hexagon's perimeter. Now ask students to express a hexagon's area in terms of its perimeter, p. With guidance, students should rewrite the expression replacing 3s with 1/2 p. Once this is understood, present a regular octagon inscribed within a circle, using the same variables for the dimensions. As before, after dividing the hexagon into 8 triangles, ask students to write an expression for the area of each triangle. students should recognize that the expression is the same as was figured for each triangle of the hexagon. Again, stressing that all 8 triangles have the same area, ask students to express the area of the octagon. Students are expected to multiply the previous expression by 8 and arrive at the following expression. Ask, what fraction of the octagon's perimeter does the expression 4s represent? Students should recognize 4s as representing half of the octagon's perimeter. Ask, how would the octagon's area be expressed in terms of its perimeter, p? After replacing 4s with 1/2 p, students arrive at this expression. Students may realize that, for both the hexagon and the octagon, the areas can be expressed as a product of 1/2 the perimeter and the distance from side to center. Demonstrating this once more with the 14-sided regular polygon will help students to generalize this concept. Having arrived at this expression a third time, ask students to use the expression to explain a way to find the area of a regular polygon. A variety of responses can be acknowledged as correct, but before moving forward, it is important for students to understand that the area of a regular polygon can be found by multiplying 1/2 of its perimeter by the smallest distance from side to center. Once students understand that multiplying half the perimeter by the distance from side to center will calculate the area of any regular polygon, ask them what a regular polygon looks like as the number of sides continues to increase. Students will likely point out that a regular polygon looks more and more like a circle as the number of sides increases. At this point, present the area formula for regular polygons once more and give students the opportunity to make connections between specific measurements of the regular polygon and circle. In doing so, they will begin to derive the formula for the area of a circle. Ask, looking at the circle, what does half the polygon's perimeter resemble? Students should respond that it resembles half of the circle's circumference. Follow with, what does the distance from side to center resemble? Here, students should see that it resembles the circle's radius. Once this formula has been completed, explain that a circle's area can be found by multiplying half of its circumference by the radius, thus addressing the second part of Standard 7G4. With this approach, students are led to construct and discover a formula for the area of a circle using concepts with which they are already familiar. Ideally, this instruction would precede teaching of the formula area equals pi r squared, as it is likely much more effective if students are given the chance to be intrigued with this new idea of finding area of curved shapes. Equipping students with the final result ahead of time could work against this goal and detract meaning from the discovery process. So instead, allow them to encounter the standard formula for the first time when they piece it together themselves, with guidance. Consistent with this focus on understanding, ATI offers a variety of items for assessing these concept-oriented Common Core standards. For example, in order to ensure understanding of Standard 7G4, this item may be included on an assessment exam. Here, students are not tested on whether they can recite or use the formula area equals pi r squared, but instead whether they can understand or can visualize the area of a circle as a product of half its circumference and radius. The same is accomplished with this item, where students are required to demonstrate the relationship between area and circumference symbolically. In addition to areas of circles, Common Core requires students to understand formulas for other measurements, such as volume of pyramids and spheres, which, like the formula for area of a circle, are not easy to explain with just a glance. In this case, though, it is important to note that in both of the standards shown, a specific approach is required, namely use of Cavalieri's principle. Realizing that this concept is sometimes explored but rarely state-mandated, ATI has developed and continues to develop resources that will assist both students and educators in the pursuit of proficiency with these standards. One of these is an instructional dialogue designed to help students understand Cavalieri's principle and the circumstances where it can be applied. Also available is a teacher's version of the dialogue, containing instructional notes and commentary to assist instructors presenting the material. Similar to items shown earlier, items connected to this instructional dialogue go beyond requiring students to state Cavalieri's principle. In addition to requiring students to recall key words and phrases, these items are designed to reinforce understanding of the concept, when it can be applied, and how it should be applied. ATI has many items that are carefully crafted to assess understanding of geometric concepts, a quantity which continues to grow. Our mathematics writers share this philosophy that understanding and procedural skill are equally important, and are therefore dedicated to producing conceptual content clearly and in meaningful ways. Know this formula, understand it, and use it expresses a goal of Common Core standards when it comes to geometric measurement. ATI understands that this middle part brings about some new challenges in the classroom. Our instructional and assessment tools were created to assist you in this challenge, so that your transition toward concept-minded content is not a grueling experience, but rather an enriching and rewarding one.